Welcome to another exercise from the workbook Statistics, this time focusing on stochastic inequalities. If we take a look at the exercise, here we have in Germany the average household income is 1,600 euros. That's the only information we get. In our task now, estimate the probability that the income of a randomly selected household will be higher than 2,000 euros. Secondly, estimate the probability that the income of a randomly selected household deviates more than 100 euros from the average. With the additional information, the variance of the household income can be assumed as 2,500 euros squared. The interesting thing here, at this moment, we do not know anything about the distribution. We simply know the average, and then the second part, the variance. That's everything there is. So let's start with the first part. Here, whenever we are asked about, and I'm going to skip ahead, that a variable should be or the probability that a variable will be larger than any particular value, we can use Markov's inequality to give a good guess about this probability. Well, what does good guess mean? In this case, we only know we have an average. So we basically know nothing at this point. But applying the Markov inequality, which simply states if I want to know the probability that a random variable is larger than a given value a being here 2000, then I can say that this probability will be smaller than the average divided by this a. So in our example, the average is 1,600, the value a is 2,000. So I know, by simply dividing these values with each other, that this probability will be smaller than 80%. Well, considering that I can have any crazily skewed distribution underlying all of this, this is a pretty good guess. However, if I just consider that this might be more or less normally distributed, then this is a pretty poor guess, because I already know that only 50% of all observations with a normally distributed variable are larger than this value. Now I'm even further away from this value. So with a normal distribution, this goes down below 50%. But here I do not know anything about the distribution, and that's the neat thing about this. So this gives us a neat, interesting insight without any additional knowledge but the average. For the next part, for part B, I have a little bit more of information. That's why I can use the Chebyshev inequality. Here, what I want to know is more or less that I get households with 1,500 to 1,700 euros per month. Or, that's just a reformulation which is closer to the original text, that it deviates less than 100 euros from the average. And that's the first part. By writing random variable minus average, then using these absolute bars, this is the deviation from the mean. This one should be smaller than 100. I'm going to use this way of writing it because this is actually what the Chebyshev inequality requires. In addition to this, what I also know is on the one hand the average of 1,600 and the variance of 2,500. Using those two values, I can apply Chebyshev's inequality, which in this case is simply this probability will be larger than 100%, or 1 minus variance divided by this deviation squared. So in this case, I'm going to go with 1 minus 2,500 divided by 100 squared. 100 squared is 10,000. So here I'm getting 1 minus 2,500 divided by 10,000, so giving me 0.75, so 75%. So I know that the probability will be larger than 75%. So they're relatively close to this value, with 75% already being in this area plus minus 100 euros. Well, that's everything there is. So I can use Markov if I only have the average, want to know how does this calculate for values being larger than a certain value. And I can use Chebyshev's inequality if I already also know something about the variance and want to know how does this work out if I deviate by a certain amount from an average. Well, that's the average thing I wanted to do in this unit. So I hope you enjoyed it. I say goodbye and see you next time.